Okay, this is our lesson on complex numbers, which is for section 4-8 in our textbook. Before we talk about complex numbers, I like to review what you already know, which is our real number system. Okay, everything that you've had to date can be summarized in this chart. Oopsie. In this chart with the set of real numbers. Okay, so when you were very young, the first set of numbers that you learned were called the natural numbers. Okay, I have 1, 2, 3, whatever many cookies on my plate. And then when you got a little bit older, you knew what it meant to not have any cookies, and so you added the number 0 to it. 1, 2, 3. Those are called our whole numbers. And then we have integers, and integers are when we started adding the negatives, positive and negative whole numbers. So it goes such. I'm trying to not hide the word here, so as you see. And then we have the rational numbers. You got a little bit older and you learned what those rational numbers were, and they were any number that could be written as a ratio of two integers, a over b. So that's your fractions. 1/2, and that does not say 1/2, sorry. 1/2, which is a terminating decimal, or you could have 1/3, which is a repeating decimal. We'll put the line over it. Okay, those should be familiar rational numbers with you. And then we have something that are irrational numbers. Irrational numbers would be something like the square root of 2, any decimal that does not repeat. Actually, that's not what I wanted to put there. 2, 1, 0, 1, 1, 0. This decimal doesn't repeat. There's a pattern to it, so you can figure out what it's going to be, but it doesn't repeat. So a non-terminating, non-repeating decimal, any kind of a radical. Another one you might be familiar with is pi, and later on we'll talk about one called e. Those are all irrational numbers, and those are all of what you know thus far, hopefully. So today we're going to talk about this, or just let you know that that set of real numbers is actually a subset of a larger set of numbers called the complex numbers. Now, these complex numbers, the set is based on a number whose square is negative not 1. Okay, that means the square root of this number is the square root of negative 1, and we call that I, which is the imaginary unit. Now, what you have to know when you're doing this lesson, you have to know how to operate with it, okay? We don't do many applications here at math. That's saved for physics and engineering, and there are lots of them that have given us lots of advancements in the world. But right now, you just need to know how to operate with it. So, first off, the square root of a negative number, okay, when this is the detail of how it is split up. If you see a negative number underneath a radical, think of that as negative 1 times any number, and the square root of negative 1 is I, so it simplifies to I square roots of A. So if I have negative 5, I just need to pull that out, pull out the negative, put it in front, write it with an I, and leave the number underneath, if it's not a perfect square. Okay? Now, because what you're going to remember every single time is I squared is equal to negative 1. That's the concept that you need to keep inside, keep in your brain. So if I have the square root of negative 5 squared, then I bring out the I, because this we just did was I square roots of 5, so I simplified the middle to I square roots of 5. Then you have to square both of these. So you square the I and you square the radical, giving you I squared and 5 squared. I squared we just said is negative 1. And the square root of 5 squared is 5. So this becomes negative 5, not positive 5. So be careful of that. But just look at some of the examples to stop that from flashing. Okay, so how do you write each number in parts A through C using the imaginary unit I? So I see a negative. Okay, I'm going to actually go down here and do it. All right. This is, first off, if I have a negative underneath it, I'm going to write it as I square roots of 12. And then going back and reviewing what you did in Algebra 1, 12 is the square root of 4 times 3. And 4 is a perfect square, so we can take the square root of 4 out. The square root of 4 is 2, so this becomes 2I square roots of 3. Okay, look at the next one. We have the square root of negative 25. Again, you're thinking square root of I, because whenever you see a negative underneath, bring it out, put an I in front. And now what's the square root of 25? It's 5. So when we don't have a radical, then the number comes first and the I comes last. But generally we put it before a radical, so there's no confusion about it being underneath the radical. Okay? Part C says the square root of negative 7. Again, I'm bringing it out. I square roots of 7. Okay, 7 does not have any perfect square factors, so I'm done at that point. It's just I square roots of 7. Okay, but look at part D. Part D says, explain why the square root of negative 64 does not equal negative square root of 64. Well, as we just did, this, okay, is I square roots of 64. So I'm working down the left side, and the square root of 64 is 8, so this is 8I. But on the other side, okay, that negative stays there, and the square root of 64 is 8. So hopefully you can see that 8I does not equal negative 8. So that's why those two things are not equal to each other. Okay, so going further and talking about our complex numbers, okay, they look like, I gotta go down some here, extend. Okay, so they look like they're always in the form A plus BI. I like that, so you can easily see that on your paper. And A is referred to as the real part, and BI, hopefully you can see, is called the imaginary part. Okay, now if B is 0, there is no imaginary part, and that's what we have everything that you've seen thus far, which means it's a real number. But if A is 0, but B is not, then that's when we have what is called a pure imaginary number, not so much complex. Okay? So, I didn't want that last thing. Go away. Alright, so let's let's go to see what we have to do with that. Alright, so the other thing that you have to know how to do in a complex number is we have to know how to graph, and we graph them on what is called not our normal coordinate plane, but a complex number plane. Okay? And what's different about a complex number plane is that the first part, which is the real part of the number, is graphed on the real axis, and the second part, which is the imaginary part, is graphed on the imaginary axis. So if I have a point AB, it represents the complex number A plus BI. Because if it's on the complex plane, then this is the real part, this is the imaginary part. Okay, y'all, this is a definition, not so much something you have to spend a lot of time going, I don't understand. You just have to accept it. Just when I give you any kind of definition, any new definition in any class you have, this is how it's defined, so you got to accept it and know how to use it. All right, so another thing that we have to know about complex numbers is something called the absolute value of a complex number. It's a little bit different, okay? And what it is it represents, just like it does in the real world, it represents the distance, but it's always from the origin. So when they have graphed this number 3 minus 2i, 3 is the real part, so we went over 3, minus 2i is the imaginary part, so we went down 2, so we get to a point. And this red line is what is representing the absolute value of that complex number. How do we find that absolute value? Well, hopefully you can see it looks very similar to the Pythagorean theorem. So we write it, you write it, looks just like normal. A plus BI, absolute value of that, equals just what you would think from your Pythagorean theorem, the square root of A squared plus B squared. Now notice, y'all, that I'm ignoring the I in this part. So when we do that, you will see that I does not matter. It's just telling us how to graph the number. So let's go do some of these. First off, what are the graph and absolute value of each of these numbers? So the first one, 5 minus I. Okay, remember this is the real part and this is the imaginary part. So I'm going to go 1, 2, 3, 4. Good move. There's no, let me move that down some. Okay, this I'm going to put R over here. So I go 1, 2, 3, 4, 5, and then I go down 1. So it's actually going to be right here. And that's my point. And I have to find the absolute value of it. And the absolute value says the square root of 5 squared plus, what is the coefficient in front of that? Hopefully you said 1, so that's 1 squared. And so the square root of 5 squared plus, that's 25 plus 1, 26. So this is the absolute value of that number. And this is where we graph the number. All right, let's do another one. We have negative 3 minus 2i. So negative 3, this is my real part, this is my real part, this is my imaginary part, real, imaginary. So I'm going to go left 3 and down 2. And here's my point. And to find the absolute value, I have 3 squared plus 2 squared. Now you might say, doesn't that negative matter? It doesn't matter because I'm going to be squaring it anyway, and when you square a negative number, you get positive. So please don't put the negative in there. It's going to make people mess up who don't remember that when you square a negative, it's positive. So you just have to worry about the numbers. 3 squared plus 2 squared, and that is, of course, 9 plus 4, which is 13. So the absolute value of this complex number is the square root of 13. All right, the last one we have 1 plus 4i over 1 up 4. Puts it right here. Make it big so you can see it. Absolute value is the square root of 1 squared plus 4 squared. And so that gives me the square root of 17, because that's 1 plus 16. Okay, so that's graphing them, talking about the absolute value. Now we're going to talk about adding or subtracting them. Okay, and this is very much like what you've already done before. So when you are adding or subtracting complex numbers, you combine like terms, just like when we add terms in with everything else that you've done so far. So that means you're going to combine the real parts together, and then you're going to combine the imaginary parts. But you do each of those parts separately. You find the ones that are like. So what is each sum or difference? It's a sum. I don't really need the parentheses here, but this is the real part and the real part. So 7 plus negative 3 is, I'll put it down here, 7 plus negative 3 is 4. And then I'm going to go back and get the imaginary part, and this is negative 2i plus I, and negative 2 plus 1 is minus I. So my answer is 4 minus I. All right, let's look at B. Okay, B is over here. All right, I have a minus, and if you have a minus, you want to rewrite that and say that's minus 3 plus 2i. Okay, because that negative has to distribute to both of these. So my real part is 1 minus 3, and 1 minus 3 is negative 2. And then let's go to the imaginary part, which is plus 5 plus 2, and that's plus 7i. So part B is going to be negative 2 plus 7i. And I probably should, let me see if I can move this. Nope, it's not all going to go. There we go. Let's move it over here since that's where part B is. Okay, let's go do part C. Again, I have a negative sign, so I'm going to distribute this negative to both of them. This becomes minus 8 plus 6i. Okay, so when I do part C, I have 8 minus 8. Okay, that's 0. We don't need to write the 0. Okay, then we go to the next part, which is going to be 6i plus 6i, and 6 plus 6 is 12i. So the answer to that problem will be 12i. All right, and let's look at that last one. We have real parts. Negative 3 plus 3, it goes away. And then I have 9i plus 9i, and 9i plus 9i is 18i. So add the real parts, add the imaginary parts, okay? And that is whether you are adding or subtracting, okay? You just have to remember that when you subtract a complex number that you got to distribute it, okay? So now let's talk about binomials, okay? We just did a lot of that. We had a nice little quiz on factoring that you could check by multiplying everything out, okay? And how do you multiply binomials is we use that FOIL method. Okay, first, outside, inside, last. So that's when you have two binomials. Are these two binomials? There's no plus or minus in it, so you're just going to multiply just like you would anything else. So that means 7 times 3 is 21, and I times I is I squared. So what is I squared equal to? Negative 1. So this is negative 21. Okay, so I think I got a little distracted looking at the problems. But FOIL, first, outside, inside, last. So on this problem, if I start off doing, these are your first terms. First, 2 times 4 is 8. Okay, then I go to my outside terms. My outside terms are 2 and 5i. So 2 times 5i is plus 10i. Then I'm going to go to my inside terms. This is, I'll stay up here. Inside are these two terms. So negative 3i plus 4, negative 3i times 4 is going to be minus 12i. And then my last terms, these are um, first, outside, inside, last. Yep. And those are my last terms of each binomial. So negative 3i times positive 5i is negative 15i squared. Okay, so when you go back to finish this problem, okay, this right here, if you have an I squared, that's negative 1. So it's changing this term to really being plus 15. So 8 plus 15 is 23. And then 10i minus 12i is minus 2i. So my answer becomes 23 minus 2i. Now, this one, I hope y'all are all looking closely, but if you notice, this is a lot of like what we just did. This is A plus B, A minus B. These two terms, okay, we've talked about that before. They look exactly the same. The only thing different is the sign in between them, okay? And if you remember that word, if we had it, I'd ask you a candy question and tell me what the name of these terms is called. They're called conjugates, okay? And when we multiply conjugates, I hope you know that that is, oops, lost my cursor, a squared minus b squared. So if you can recognize that, when you multiply these out, okay, that means that I'm going to have what's a in my problem is negative 4 squared minus 5i squared. Well, negative 4 squared is 16. 5i squared is 25i squared. And what did we just talk about? When you have an I squared, it actually ends up changing that. So this becomes 16 plus 25, which is 41. So what's most important about that And what you need to remember, okay, is that when I multiply these two things that are conjugates of each other, notice that you're squaring the first term and you're squaring the last term and you're adding them, but I really want y'all to see that our I has gone away. So when we multiply two complex numbers that are conjugates, we get rid of the I. And that's kind of a really important concept of what happens when how we divide and what we're going to use them. So just to emphasize that, the factors a plus b and a minus b give us the product of a squared minus b squared. And these factors, as I just said, are called conjugates. And complex conjugates, which means they're going to have that I in them, just like the problem we just did, are a plus bi and a minus bi. And their product always gives us a real number. So I'm just kind of putting in English what we just talked about. Okay? And we use complex conjugates to simplify quotients of complex numbers. What's a quotient again? That's when we actually have to divide. Okay? So, what is each quotient? When you look at this, you have 5 minus 2i, 3 plus 4i. Well, we cannot leave an I in the bottom. So I have to get rid of that. And the only way to get rid of it is to get I out of here. And I do that by multiplying the top and bottom by the conjugate of the denominator. 3 minus 4i over 3 minus 4i. So now, when you multiply that, on the top, remember I said you square the first number, add it, and square the last number. Now, if you want to see that more detail, come see me because I just did that on the last page. So I'm trying to not make the video so long. So, FOIL, 5 times 3 is 15. First term, outside terms. Actually, it's minus. 15 minus 5 times negative 4i is negative 20i. Inside is going to be negative 6i because it's minus 2i times 3. And the last term is going to be plus 8i squared. And remember, we've talked about that I squared ends up changing this, and it makes it look like minus 8. So now, when I go to simplify this, all right, on the top, I'm going to have 15 minus 8, which is 23. It's not 23. Good move. 15 minus 8 is 7. Minus 20 and minus 6 is minus 26i. And then 9 plus 16 is 25. And the only thing you have to do is you always have to write it in standard form. And the standard form for a complex number is always a plus bi. So that means I just need to break it up and write each of them underneath that denominator, or excuse me, on top of the denominator. So this becomes 7 over 25 minus 26 over 25, and then I put the I like that. Make sure you don't put it in the denominator, but that's your A and that's your BI. Okay, let's look at another one. Let's go with a different. Let's try this. Keep that straight so you can see. Okay, so this one, if you notice, I don't have a plus or minus in the bottom. So really, the only thing I have to multiply here is an I to get rid of the I in the bottom. Okay, so on the top, 4 times I is 4i, and I times I is I squared. And on the bottom, I have 6i squared. So when I simplify that, that's going to give me, this is going to be plus 1, because that's minus negative 1, because I squared is negative 1, so that becomes plus 1. And we write that part first. So I'm going to write 1 plus 4i over I squared is negative 1, so this becomes negative 6. And then putting it back into standard form, that gives us negative 1/6 minus 4 over 6, which is 2/3 I. So that is what that result looks like. Okay, and another one. Let's try that. I hope I left enough room here. All right, so let's look at 8 minus 7i, 8 plus 7i. So I'm going to stop for a second. Hopefully you can tell me what do I multiply by. Pause if you don't know. The conjugate of this bottom. So that's 8 minus 7i over 8 minus 7i. So on the top, or I'm going to do the bottom. The bottom, you square the first number, 64, plus square the 7's, 49. Okay? And now I'm going to multiply out. You can do your PST, or I'm going to go ahead and FOIL because I think most people will like that better. So 8 times 8, 64. That's my first term. Outside term is minus 56i, 8 and negative 7i. Inside terms, negative 7i and 8. And last terms is minus times minus is plus 49i squared. Okay, and again, when I see I squared, it's a negative 1, so it changes that sign, so this thing is really minus 49. So now, when I write this one, um, on the bottom, 64 plus 49 is 113. And I have 64 minus 49 is 15. Negative 56 and negative 56 is negative 112i. And again, put it back in our standard form, so I just have to write each one. 115 over 113 minus 112 over 113, and then I put the I out. So it's easy to know which is the real part and which is the imaginary part when you write that like that. Okay, so hopefully you got from that, and what we were just doing is you got to remember to never ever leave I in your denominator. Okay, so that's what we were just doing. All right, now look at the difference here. We're going to keep doing what we have done before. What are the factored forms of each expression? But this time, we're going to be able to factor them over. Okay, so this time, because they asked me to factor them, we're going to factor them over the complex numbers. And that means, okay, first thing we're always doing, looking for a GCF. So 5 times x squared plus 4. And before you thought that was prime because we were dealing with real numbers. But when you do it with the complex numbers, this is a perfect square and that's a perfect square. And what allows us to factor that is doing x. It's still going to be the square root of negative 4, which is 2i, and then x. One's minus and one's plus. So that's factoring it over. And if it helps you, you might think of this as this is really 5 times x squared minus negative 4. And we've talked about earlier the square root of negative 4, that's where you're getting the 2i and the plus or minus the 2i and why it becomes that. But more importantly, if it ends up as plus, just know that the factor has to be, well, look at this one. If this said x squared minus 81, then you would know that's x minus 9 and x plus 9. Okay, but since it says minus, what's going to change about my problem? Okay, I'm still going to do x minus 9 and x plus 9, but because that's a plus, I'm going to put the I with it, and that will take care of making it x squared plus 41. Okay, so the last thing we have to do is bring this together with solving our quadratic equations. Solving, and then I'm going to show you a little tip. Okay, so every quadratic equation has complex solutions. You just haven't done it thus far in your life. But every quadratic equation, has complex numbers as solutions, and that are sometimes real numbers. Because every real number can be written as a complex number. Okay? If you had a solution that was 4, y'all, that could be written as 4 plus 0i. So this is a real number as you've known it before, but it's also a complex number. So that's just an example of why everything you've done before is really that. We're just expanding. Okay, so what are the solutions of this problem? Um, you can try to factor it, but I'm going to save you some time and tell you that it can't be factored. So I'm going to use the quadratic formula. A equals 3, B equals -1, and C equals -2. So in my quadratic formula, A equals all over 2A. Okay, it's the opposite of B plus or minus the square root of B squared minus 4 times A times C. Now notice, remember I always think it's important to put parentheses around the negative numbers, not so much with the positives, just kind of a habit that I have. Okay, so as we continue that, x equals -1 is +1, plus or minus the square root of, well this is 1 plus, b is -1, c is not -2, y'all. Nobody's here to fix me up on that. So let me correct that real quick. So this is not, c is +2, +2. So this becomes 1 minus 24, and 1 minus 24 is -23. And on the bottom I have 6. So you have that negative underneath. That means that, extend that just a wee bit, just to here's fine. X equals 1 plus or minus I square roots of 23 over 6. I see a negative underneath. I'm going to bring it out front, make it I, and then deal with the rest of it. Okay? And again, hopefully you can see that's coming from the quadratic formula. To write it properly, you would break it up if I asked you to write it as a complex number, and in which case this would become square root of 23 over 6i. Okay, keep in mind either one of these is acceptable, and I really want you to know both of them. I want you to understand that these say the same thing. So your book might have it like that, or they might have it like that, and whichever way you have it, that those are the same thing. Okay, so keep that in mind. Now, this next one, you can put it in the quadratic formula, but I want to show you something else about it. Whenever b is an even number, it's not a hard problem to solve by completing the square. So kind of review that method. X squared minus 4x plus something, have to take that 5 over there, equals -5 plus something. Okay? Because I wouldn't do it if this was an odd number because you're dealing with fractions. But we're not. So to complete the square, I take 1/2 of that number, which is 2, and I square it, and I write that out over here. So when I factor that, that becomes x. Always take something from each term. So that's the square root of that is x, the square root of this is 2, and we take the sign from the middle number. So x minus 2 squared equals -5 plus 4, which is -1. And when I take the square root of both sides here, then that means that I'm left with x minus 2 equals plus or minus the square root of -1. And hopefully you see that x minus 2 is plus or minus the square root of -1 is I. And to solve for x, I have to take the 2 over, so x equals 2 plus or minus the square root of I. Now, would you get that if you still solved with quadratic formula? Absolutely. Would you be able to factor it? No, because they're not real numbers. They're not the whole numbers that we're used to using with our factoring. Okay, I'm done with that. I have a little bit of a chart here, a pattern to kind of help people and make them be aware, because I like to put these things on the ACT, SAT, of how to simplify complex numbers. Okay, there is a pattern, and I'm kind of hoping that you can recognize this pattern. Remember, I is equal to the square root of -1. So when you see I in a problem, you're done. You leave it as I. Okay? But other than that, you never ever want to leave an exponent on I in a final answer because it can always be simplified. So if I equals -1, then when I square both of those, we know that I squared is equal to -1. So I squared is -1. That was our definition from way back in the beginning. Okay? Well, next, what if I have I cubed? Well, I cubed is just I squared, excuse me, I cubed is I squared times I. So it's these two multiplied together, which is -I. And then I to the fourth is just I squared times I squared. Well, what's I squared is -1, so -1 times -1 is 1. And then if I go again, I to the fifth. Well, I to the fifth I'm going to say is I to the fourth times I. Well, what was I to the fourth? I to the fourth was 1. 1 times I is I. And then I to the sixth. Okay, so when I get to I to the sixth, I'm going to write that as I to the fourth times I squared. Okay, I to the fourth is 1 because every time you have anything that's the fourth, it's gone. So I'm left with I squared, and I squared is actually -1. And I messed up my pattern. Let me fix that, y'all, because I want you to be able to see this. Okay, so that's I to the fourth times I squared. I squared was -1. I to the fourth is 1, so I'm back to -1. All right, I to the seventh is I to the fourth times I to the third. Well, what's I to the third? -1. I to the fourth is 1, so we're back to -I. I to the third is -I. I to the fourth is 1, so when you multiply together, you get -I. And then I to the eighth, last but not least, I to the fourth times I to the fourth. I to the fourth is 1. 1 times 1 is 1. So I'm trying to show you that every 4 times there's a pattern. I, -1, -I, 1. I, -1, -I, 1. It is repeating every time. So what's really important to remember, if you can see that, is if it has an even, this is with your exponent, if it has an even exponent, then it's always going to be an answer of 1 or -1. If it has an odd exponent, it's either going to be I or -I. So every time you simplify an expression with I in it, you always want to think about how many times 4 goes into the exponent because I to the fourth is equal to 1. So I'm going to write that again. Okay? I to the fourth equals 1. So does 4 go into 28? It goes in 7 times. So this is the same thing as I to the 28th because when you raise a power to a power, you multiply. So I to the fourth is 1, and 1 to the seventh power is 1. So this becomes 1. Look at I to the 51st. How many times does 4 go into 51? Because we're thinking about I to the fourth. And 4 goes into 51 12 times. That's 48 with 3 left over. So here's my 1 times I to the third. And I to the third, we just figured out, is -I. Okay, 2 more before the onslaught. I to the 101. Okay, so I'm going to do I to the fourth. I'm always trying to figure out how many times does I to the fourth go into it. Well, 4 goes into 101 25 times with 1 left over. So my answer is just going to be I, because that's what I have left over. All right, last one. I to the 254. How many times does 4 go into 254? It goes 62 times. How many are left over? 2. So if I have 2 left over, that's the same thing as I squared, and I squared is -1. So lots of information for you to absorb. I hope that you will practice, do your problems, refer back to any part of this video if you need to, but more importantly, please come see me if you have any questions. Thanks for listening.